So who wants to go first?
I don't have a specific question, but I still get confused on IR spectrums and identifying functional groups in them.
So let me, I'll try to draw something qualitative on here, but I'll put some functional groups up there and sort of point out the key things and how the spectrum might look. So say, for example, say you were given these two molecules. So you're given, what are these, C4 molecules. They each have one main functional group, and those functional groups are going to be pretty different by IR. So the first thing you should do, I encourage you on the exam, you get to keep the exam. Again, the only thing I need is the signature sheet and the actual if-at form. Write stuff down. Write stuff down. I can't state it any other way. A lot of students in organic just try to keep it all in their head, and you're most likely going to be presented with more than one concept. So if I'm approaching this, how would you differentiate these by IR? What functional group is in this compound here to the left? What's that?
Is it carbonyl?
There's a carbonyl. So of that class of carbonyls, what can you narrow it down a little bit more?
Is that a ketone?
It is not.
Is it an aldehyde?
It's an aldehyde.
I knew it was one or the other.
So the compound to the left is an aldehyde. So I'm just writing that down. It's an aldehyde. That's one less thing I actually have to remember. It's down. So when I look at the compound to the right, what functional group is in there? That's an alcohol. So again, as I've underlined in red there, that's the functional group word. And then what you're seeing here, O double bond C, and the H, that's the aldehyde. COH, that's alcohol. So there's the different associations you want to make. And so the carbonyl stretch is always going to occur about 16 to 1800. So there's like 7 functional groups that have carbonyl. So if you see it there, you can say, okay, it's one of these, but then you're going to have to use some other piece of data to really narrow it down which one exactly it is. So what does a carbonyl actually look like? So here's an abbreviated spectrum. So you're looking between 16 to 1800 reciprocal centimeters. And again, at the top of this spectrum, like nothing's happening. That's 100% transmittance. Then the laser is going to hit that dipole moment. So that's what's being excited in the IR experiment. You hit the dipole moment, and then when it dips down, that's absorbance. So carbonyls are usually pretty strong. So this is the actual the dipole moment being excited in that molecule. Do you remember where an alcohol OH stretch would occur and what it would look like?
It's farther left, isn't it?
So it's more left along the spectrum. So if you look on the handout, I divide the IR into 3 regions. Region 1 is the CH, OH, and NH stretching. the OH stretch is going to be pretty broad. So usually between 3,500 and say 3,000. And so that's going to come along dip, be pretty broad. At that point, it's going to go back up, and then it's going to hit into the CH stretching, which is the stuff that pretty much every compound has. So CH, and then this is OH. My best advice for this is just look at those spectra. And there's specific things you're looking for each functional group. If you go on sapling, I think it's like the third thing down in your home page. There should be like 3 links to websites where you can do spectral problems. So these are just like, they're not from any particular book. Just click on them, you're given some information, and can you figure out the spectra? So again, to recap, the main thing for IR. So it excites the dipole moment. And it's telling you about functional groups. So I'm sure we'll revisit the IR question at some point over the next hour. Why don't we move on to another question?
Could you go over it any more?
So the question was NMR. So I have a book. This is not your book. It's an organic book. You can use any organic textbook for this class. Just open up the table of contents. You'll see the chapter headings are pretty similar to what we talk about. Flip open to the whatever chapter and just do problems. So I flipped it over to NMR. I'm going to pick a problem, and then I'm going to ask you guys some questions. So as Arnold Schwarzenegger says, you're going to want some answers. So let's pick out, so here's a problem. So this is going to be both proton and carbon. So I think, was it a tutorial center today, or maybe I said proton and hydrogen? Those mean the same thing. So if there's a misunderstanding, I apologize. But when I say proton NMR, hydrogen NMR, it's the same thing. So here's a problem in this book. And it says, predict the multiplicity of each signal in the proton NMR of the following compound. So I'm not going to just give you the answer. I'm going to pose some questions. I want you to think about it. And then if you're, like I said, confident, just throw the answer back at me. The first thing, anytime you're given a structure like this, I think I have like a laser feature on here. Oh yeah, look at that. So anytime you're given a compound like this, figure out the molecular formula. So let's do that first. So what's the CH and O count in this? So C, what is going on there? C11. H how many?
21.
I don't quite agree with that. So 22. The reason I hesitated is because the number that you gave me was odd. And there is a rule that I could tell you, but I don't want you like sort of memorizing that. So you have one oxygen, all carbons. The proton count is for the most part going to be even. Only when you start introducing nitrogen can you have an odd hydrogen count. So we have H22 and then one oxygen. What?
Oh, I thought you were asking what.
Oh, so there we go. We have one oxygen. So before we get into the proton and carbon, let me pose another question. If this was a mass spec problem, you're given this, you found the molecular formula. What would the parent mass be of this? Do you know how to do that? So why don't you bust out your calculator app, throw a number at me, and then we'll see if we're all on the same page with that. So is that right? We took 11 times 12 plus 22 times 1 plus 16. So I'm taking your word for it. So that's the parent. That's the mass that corresponds to that fully intact molecular formula. So let's go through the usual exercise. How many unique carbon signals would you expect to see for this molecule? You said 10. What do you say? I'm gonna put you under the hot lamp here. Sweat it out of you. What do you say? I don't know is. You say 8. You say 10. You say I don't know. I don't want to sound facetious, but choices A, B, C, or D. None of them will be I don't know. So I would say at some point just commit to an answer and be comfortable with being wrong, because we'll talk about the wrong answers, why they're wrong, and why the right answers are right. So we have 8 versus 10. Maybe we can form a consensus. What do you say?
Originally I was saying 8, but then I counted again and I counted 7.
So 7, 8.
I counted again and I got 9 the second time.
Ooh.
I'm sticking with 8.
Sticking with 8. I'm going to say 8. So I'll change the color here. We'll go to red, and I'll put a dot by each unique one. So this and this are the same, right? So that's 1, 2, 3, 4, 5, 6, 7, 8. Yes.
Okay, 1, 2, 3, 4. I'm confused how, I don't know how to describe where the location is, but it's like the O double one and then it goes out like this. I would think that those two would be the same because they have symmetry. Are they not?
So let me redraw the molecule, because I am recording this, so I can point out on here what your question was for if people watch this later. So you're asking about that and that, and basically why they're not counted is 1, why they're different.
I see now because this one is connected to a different carbon and this one. Right.
Yeah, so if you look at this one, so this goes to the first part of your question when you said I don't know how to describe it. So a group that has 2 protons, a CH2 group, is secondary, and it's called a methylene. So that's a methylene group, as is that. This group's called methyl. The group with just a CH is called methine. So I'll point that out. But it appears that you found or discovered why they're not the same type of CH2, right? So as you go out CH2, but then as you go out again, now that next thing is different. So that means those cannot be the same. So let me write these out so we're all on the same page. And again, I sat through a PhD defense last Thursday, and the student was struggling to describe the location within a molecule. And what I'm about to tell you is how you would describe things. So if I said, go out to Hardy Street, make a right, go over 59, those are sort of directions. So this is a methyl. Methyl is CH3. So within this molecule, you have 2 types of CH3s, right? You have these, and you have those. CH is called methine. And CH2 is called methylene. So again, none of you are going to become organic chemists, but you are going to go into some special area and learn the vocabulary of that discipline. So it's really just about, are you able to assimilate, a new language in a way. So I would say the methylene group next to the carbonyl. The methine group 2 carbons away. So the long answer for this is we have 8 unique carbons. So let's dig a little bit and talk about the protons now. Let me sort of back up just a smidge here. We see that we determine there's 11 total carbons, but there's only 8 unique carbons. And again, that's due to the symmetry. So that symmetry there reduces the count. This symmetry there then reduces it by another 2. So what about the unique number of protons? I heard the start of the correct syllable. Yes, it's 6. Does anyone count differently? The reason you get 6 and not 8 is because you have 2 carbons that are not bearing hydrogens, right? This carbon right here, so that's another type of carbon that I haven't mentioned yet. A carbon bearing, back up, an sp3 hybridized carbon bearing no hydrogens is called quaternary. So that carbon has no hydrogens, and then obviously your carbonyl carbon has no hydrogens. So that's why you further reduce the count. So we have and now can you tell me the ratio? Ratio is another word for when you actually look at the data. It's called integration. You're actually looking at the NMR spectrum. instead of the word ratio, we're going to say integration. What is the integration of that peak? And all it is the number of protons belonging to that peak. So if we're looking at this structure from left to right, let's write the ratio that way. We'll consider all these moving from left to right.
Left to right.
Yeah, if you're looking at, if we're going to write the ratio, we're looking at all the unique sets reading it this way. What's the first number I should write? 9. See how these methyl groups, they're all the same, 3, 6, 9. What's the next number? 2. Two. So there we go. So if we verify that, the sum of that has to equal this count right here, 22. So we have 9 plus 2, it's 11, 12, 13, 14, 15, 16 plus 6 is 22. So the sum of that has to be whatever you counted initially. So let's dig a little deeper on this one. And that's the exciting thing for me as an instructor, because I can always keep asking questions. It's the frustrating thing for you as a student, because it forces you to think a little bit harder, right? So we've done this approximation, there's 6, this is the ratio. Now let's describe what these peaks are going to look like. Because initially they're just going to be 6 sets, but what is the peak shape actually going to look like? For these 9 hydrogens, these 3 methyl groups, what should the shape of that peak look like? And again, this is where you use that n+1 rule. So what you want to consider, maybe what I'll do is I'll draw like a first approximation and just show you sort of what I'm thinking and how in a second approximation that would change. So not too bad for the spacing, I guess. So the chemical shift is the distance away from 0. These are all pretty much going to be bunched up between 0 and 3 based on what they're bonded to. So maybe what I can do is sort of running out of space here on this page. I guess just start another one. So let me just redraw that. So we said 9 to 2 to 2 to 6. So here's what we mean by that. We have a peak at a first approximation that's going to be 9. You have another peak. Try to draw this sort of, that's going to be 6. Then you have say a 2, a 1, and then these other ones are going to say 2 and 2. So all this is what I'm indicating. We have 1, 2, 3, 4, 5, 6. That's the ratio of them. But they're not actually going to look like that. These 3 methyl groups are the same. They integrate to 9. If you were just considering one of them, and I'm highlighting it, and you look over, so each of them has 3, so it doesn't matter which one you consider. You look over to this carbon. How many hydrogens are on this carbon? There's none. So none plus 1 is 1. So these 3 are going to look like a singlet that integrates to 9. So from your first approximation to your second, that's not going to change much. So I'm just going to sort of draw it. So I put some like area under it. Let's go. We'll sort of flow in order the way that I've written them. Now we're going to look at these 2 here, this methyl and that methyl. We said they're the same. If you look to the neighbor, there's only one carbon neighbor. How many hydrogens are on that carbon? 1. So 1 plus 1 is 2, so that's a doublet. So this peak here that we said was 6, instead of looking like that, it's going to look like a doublet. I apologize, that looks terrible. This, I haven't like drawn on this thing in a while, so. Uh-oh, that's the highlighter. So there's a doublet. So we have a singlet and a doublet. And so I said the next one's 2. And I want to assign that 2 to this carbon right here. So there's 2 hydrogens there. Look to the left, the right, the up, and the down. How many hydrogens are on this carbon? None. How many here? 2. So this is going to be 2 plus 1, so that's going to be a triplet. So this peak that I wrote as 2, instead of looking like that, it's going to be a triplet. So when you're going through this exercise, you have to consider the immediate carbon neighbor or neighbors. You have to consider them all. So that's what really stumped me about what was stumping you during the iClicker question today. So this is going to be, so we would call that a triplet. like why I wrote them in this particular order? Yes. So, yeah, that's definitely glossing over a pretty important fact. Maybe let's get through this one, and then we'll circle back to why I wrote them specifically like that.
For the neighbors, are you counting the carbon or are you counting the hydrogen?
The hydrogen on those carbons. So we were doing that one. That has a ratio of 2. There's 2 hydrogens on it. So, which means of the 4 valencies, 2 are already taken. So you have to look to the 2 other neighbors, which are carbon and carbon. So that carbon has no hydrogens. This has 2. So 2 plus 1 is your 3. So this peak is a triplet because of those neighbors.
So it doesn't necessarily matter what it is or how many hydrogens it has, it just matters what the neighbors have.
Correct. So that's the tricky thing about really understanding this. The peak you're analyzing is influenced by the neighbors. That's how you arrive at this approximation. So now here's the fun one. This is the only one that integrates to 1. So carbon has 4 bonds. One of them is the proton of interest. So the 3 other bonds are to carbon. So how many total neighbors are there now to this one? There's 8. So 8 plus 1 is 9. So let me see if I can draw a non-net or 9-et or whatever it's called. So you'd have to go really far down on Pascal's triangle to see what this looks like, right? So this 1 is going to go that's not bad. Clap myself on the back for that one. So it's pretty crazy, right? I mean, 3, 6, 8 plus 1 gives you that. So we'll write our little 1 there. And now what we have remaining are CH2, CH2. Let's do this one first.
Can I?
Yeah.
Why we didn't take into account the hydrogen that's in the
Can you point to which one specifically?
so right?
So that's the one that we are analyzing.
Oh,
So we are analyzing that one. So we have to go out to this neighbor, and that neighbor.
okay. I was looking at it wrong.
So if we look at this one, you have 2 hydrogens. So therefore you have to look at 2 neighbors. How many hydrogens are here? None. How many are here? 2. So 2 plus 1 gets you 3. That's your triplet. So I know it's a lot of information to take in, but as you'll see, there's only so many different combinations of what these neighbors can be. So you'll get pretty adept at figuring it out. So that one's a triplet. And then we have 1 remaining, which was this one right here. We already said that has no hydrogens. How many hydrogens are here? 1. So this peak should look like what? A doublet. So really what this second approximation is doing, it's taking into account how the neighbors split the original peak. So there's one last thing that we have not talked about, and we will, not for this exam, but is the distance between these peaks. That's called the actual coupling. The magnitude of that coupling tells you the spatial orientation between the protons involved. So there's always another question. So is that good for that one?
Do you mean the space in between the peaks themselves or from peak to peak, like separately?
So what I was just referring to, if you took a ruler if you put a line going down this, going down that, and then you measured that distance between them, that distance is called the coupling constant, which is abbreviated J. And so I don't want to overwhelm you with stuff, but the reason why you would consider that as a preview of what we're going to in this class, you know what this means. That carbon has a geometry. This is tetrahedral. And if you were to draw, say, this hydrogen coming out, we're eventually going to get to, with your model kits, instead of you're looking at this molecule perpendicular to this whiteboard, this screen here. You can imagine taking your eyeball and rotating it 90 degrees so that you're looking down the axis of a bond. If you can imagine doing that, you'll see that these two hydrogens sort of eclipse one another, and these two do not. And so that's going to become important to us when we start studying molecules that are rings. The ring locks it into a specific conformation, and you can get information about the coupling constant and the nature of those hydrogens. So that's probably a little bit more than what we want to cover for that. But to get to your next question, how do you know to write it in this order? So we'll do a little bit more simple molecule, and you'll start to see why these things, again, this is called the shift. Where that peak is, say that's 0.1 parts per million. That's 0.1 shifted away from 0. Why is this shifted there and that shifted to about 1? It has to do with how different it looks from methane. And so I think that brings up a nice question. We'll call this chemical shift. So assume that methane is the simplest organic molecule, right? CH4. Assume those protons are at 0. That's sort of like the baseline. Every time you remove a hydrogen and you add something, you're altering the environment of those original hydrogens. So it has to move it away from 0. So let's look at this molecule. Give you just a bit of review here. So this is an alkyl chloride. The chlorine has 3 lone pairs. I'm going to write delta minus. Then the thing bonded to it is delta plus. So how many unique type of carbons do you have in this molecule?
2.
You have 2. How many unique type of hydrogens? 2. And what's the ratio of those hydrogens?
6 to 1.
6 to 1.
That brings up like a quick, short question.
Yes.
Are we gonna have to worry about like chirality as far as like a chiral molecule?
Not in the sense that you're probably asking this question. So you probably read ahead or something. That's going to be a little bit further on. So that's the complexity. This molecule does not have any of that. For this exam, you don't have to worry about that. So look at CH4. You've removed, this is CH3. So we all know that's methyl, CH3. You've removed an H, and you've replaced it with all of this. So that has to shift it away from 0. So I know this might not completely make sense to you guys, but this is 0. This is methane. I've just redrawn it. The thing I circled is what you're substituting to make that molecule. So now that the hydrogens there have to shift away from 0. So we said there's 2 unique sets. So 6 to 1. What should be this set that integrates to 6? What should that look like? How many neighbors does it have? We said these are the same.
It just has 1, right?
It just has 1, so there'll be a doublet. That doublet, when you're reading from right to left, the doublet's going to come first, because these more resemble methane than does this hydrogen. So we're here 0, we're plugging along, then we're going to hit our doublet, and that's going to be 6. Now if we do that sort of same analysis for the next one, the carbon bearing the chlorine, I don't want to do that. So we're looking at this center carbon. It's carbon and H. So how have we gotten away from methane? We've substituted 1, 2, 3 things. The 2 methyl groups will push it a little bit further along, but what really pushes it is that chlorine, because as you determined already, the chlorine's electronegative, it's bearing this delta minus, therefore the carbon's delta plus. So if we're looking at this scale here, I would say this proton, not only due to both of these carbons being attached to that one, but more so the chlorine, it's going to shift it between 3 to 5. So it's quite a big jump due to the electronegativity of that heteroatom. So if you look at that, which integrates to 1, how many neighbors does it have?
6.
So it should be what? See if we know our Greek.
Yeah, pento? No.
Think of the months. Is that right? I don't think so. No. This would be a septet. That's weird now that I think about it, because September is not the 7th month. So anyway, so you chug along. Oop, I'm going to do red here. So there would be your septet or heptet integrating to 1. Again, the question was, how do you know like how it's going to occur on this scale? I mean, it's really what is bonded to the carbon. How do those groups influence pulling it away from 0? So you have an Apple Watch. What model is it?
Series 2.
Series 2. Does anyone have an Apple Watch? What series is it?
3.
Mine's
2, 3. So I got a 4, and this thing will do this EKG thing. Maybe I can show you guys in real time. So it's a piece of like data. So you can see how unhealthy I am. So this is a piece of data that organic chemists use. And then this is a piece of data that a doctor can use. So it might look a little weird because I'm standing up. I put my finger there. And eventually it should show a normal pattern. You guys all see that? So it's starting to get a little goofy because I moved around. So it might say I'm about to have a heart attack. So it says the ECG is inconclusive. The reason it said that is because you're supposed to like sit still and not move. But when you look at data, you'll eventually start seeing these patterns. If you want to become a dentist, you'll take 1,000,000 x-rays, you'll know what a normal tooth looks like. So that when you take an x-ray and you see something, hey, that looks strange, then you make the connection, why does that look strange? Some kid's eating too much candy. They have a cavity, you know what I mean? They have gingivitis, the gums are receding. So again, the skill is you need to know some NMR to pass this class, but the skill is about assimilating how to interpret data. What's normal and what's different. So next question. You got a sapling question?
I did have a question on sampling. It was just on the NMR. It said, what does NMR convey? I can't remember exactly what the choices are.
Does anyone else remember what they were? You guys back here have questions? No?
Okay, yours is sapling.
Maybe let's just take this up here, I'll write it down and bring it back. So it's question 22 on yours. They mix it up, so it's not going to be 22 on anyone else's. So here's what you're given. You're given a molecular formula. You're given a chemical shift of 1.5 parts per million. And then you're given a letter S, which stands for singlet. This peak is a singlet. So think about what that means. I'm like verbally telling you, but you need to process it in the sense that the peak's a singlet, so it's telling you something about the neighbors, right? And so that's what you need to like visualize. So what do we want to do first? What's the first thing you should always do?
Draw the structure.
That's going to probably be one of the last things you do. You're given a molecular formula. What do you want to do with it?
The degrees of unsaturation.
Degrees of unsaturation. So can you do that in your head, or should I go through it?
You should go.
Okay, let's go through it. So this is what you're given. So we need to figure out degrees of unsaturation. And we're going to use that formula because it corresponds to a saturated alkane. So N is 5. So we just plug that in there. C5, H 2 times 5 is 10, plus 2 is 12. So for 5 carbons, you should have 12 hydrogens, but it's clear that you don't. So C5 minus H10. So for every H2 molecule, that's 1 degree of unsaturation, so we divide by 2. Generally speaking, what is a degree of unsaturation? A double bond or a ring. So even though this was a bit sort of rushed today, the chart that I showed in class of where the functional groups fall on the scale, a double bond CH, so a hydrogen bonded to an sp2 hybridized carbon would occur at about 5 to 7. So this does not have that chemical shift. It has a chemical shift at 1.5, so that's going to rule out a pi bond. So what do you think the degree of unsaturation belongs to? A ring. So what is the name of the compound that I should draw here that's going to match all this data?
Is benzene 6?
6 carbons? Yes.
I don't want to say it be wrong.
It's fine, just say it.
But it would be like pentane.
So pentane is part of it, but it's not 100% right. So the word pentane does not.
No.
So what is it?
Is it cyclopentane?
It's cyclopentane. Because again, that's the difference. Pentane is the fully saturated. This right here would be pentane. This, what you're trying to figure out, is cyclopentane. So let's draw that and see if it matches everything we're given. We have 5 carbons, 2, 4, 6, 8, 10 hydrogens. How many unique carbons are in cyclopentane? it's 1.
Oh, when you cut it down to symmetry, there's only one.
Correct. How many unique type of hydrogen are there? It's 1. It's sort of a trick question, right? Because it's already given to you. There's 1 unique type of hydrogen. That's the chemical shift, and it occurs as a singlet. So every CH2 group in this molecule is the same.
How does it occur as a single?
Is that because if they're the same, like, they're not unique, then
So that's what's sort of like the mind F, right? I mean, you're looking at a specific one, it has these neighbors, and you're asking yourself, well, it has 4 neighbors, 4 plus 1, it should be a pentat. But this is the same as that. So it's really not its neighbor, it's the same thing. You can do that all the way around the ring.
so neighbors have to be unique sets as well.
Yes. It's like a movie called like Identity or something. This guy has like 17 personalities, but he's one person. I don't know, you should check it out. So it's sort of like you have to recognize, is it the same thing? And that's where it can get a little tricky. So that's a sapling. Do you have a sapling? You have a sapling? Do you have any other questions you want answered? We try to get everyone at least once. Okay. You have another one?
This is in like homework 2.
Okay. Okay, so this one requires a little bit of subtle recognition, put it that way. You are given what's called an empirical formula, C2H3O, and you're given a mass, m to z equals 86 AMU, which is atomic mass units.
I remember this one.
So recognize that 86 is the sum of all the C's, the H's, and the O's. So the first question I'm going to ask you, when you add up those atomic weights, what do you get? So this is the difference between an empirical formula and a molecular formula. the empirical formula has been divided by some integer. So we're going to take 86 and divide by 43. And you get 2. So what do you need to do? You then take that 2 and multiply it by that empirical formula. So what you're actually working with is that. So does everyone follow that? So those are the functional groups that you have to propose for each structure. You have to propose 2 structures. The first one has an alcohol, ether, and alkyne. The second one has an aldehyde and a ketone. What did we say the first thing we should do when we're given a molecular formula? What do we need to do?
Degrees of unsaturation.
Calculate the degrees of unsaturation. So for C4H6O2, how many degrees of unsaturation are there?
2.
And so what I want to point out next is the reason as you progress as a student, becoming more astute about like the subtle things that are like right in front of you. It's telling you to draw a structure that has an alkyne. What is an alkyne? How would you describe it?
Triple bond.
A carbon-carbon triple bond. And that has how many degrees of unsaturation?
2.
It has 2. Your molecular formula has 2. So whatever you propose here, the degrees of unsaturation have to be in that alkyne. So let's go ahead and sort of do a fragment analysis here. I'm going to say C2. I'm just going to count for the carbons of the alkyne. So we've gotten rid of that. Now what's remaining in here, you have to have an alcohol and an ether. So the alcohol is pretty straightforward. So let's get rid of that one first. What 2 elements are in an alcohol? OH. So we're left with 0 degrees of unsaturation. So now that has to have an ether in it. So there's a couple different ways you can do this. I don't know what it's going to accept as right. There are some that are certainly going to look more strange than others. But if we were to just draw, say there's 2 carbons, 1, 2. Then we put that oxygen here. We know that that oxygen has to have a second bond to it. You could say, Matt, well, I want to draw it this way. Carbon to oxygen. There's the second carbon, and there's that bond. So basically what you're doing now is putting these all together so that they're all bonded to something. So say I want to do this. I'm going to bond 1 to here, do that to that, and then do this other one, OH think I've used everything. There's an alkyne, an alcohol, and an ether. So what about structure 2? Again, it's the same molecular formula, 2 degrees of unsaturation. An aldehyde has how many degrees of unsaturation? 1, and a ketone has? So an aldehyde has to have the following fragment. Then within that, you have to have a ketone. Based on what a ketone is, the carbonyl has to be flanked by 2 carbons. So you have 3 carbons remaining. So we're going to draw it like that. The carbonyl now has to be on that center carbon. So that's the definition of a ketone. But how many hydrogens are in this fragment?
6.
There's 6. So we have to remove 1. So that's where you're going to bond it to something else. And so you're really only limited by bonding those 2 fragments together. So that would be a proposal for that one. Next question. That smoke alarm's gonna drive me nuts. I absolutely hate that beeping sound. If any of you live in apartments and you have a smoke alarm that goes off at starts doing that, you will wake up in like a fit of rage and you will rip it off the ceiling. I've been there and done that. So seeing this model kit, it's a good idea to bring your model kits during exams. You can use them. Make sure you know what sort of SP3 versus SP2 versus SP looks like in those things. I think you do have an alkyne in there. It's the one that's like gray. It's sort of longer than the other ones. Next question.
I guess how would you consider studying more for IR as far as peak memorization goes? Because there's like so many different combinations to think about. It's just
Do you have Sapling open? Can you scroll down to those websites?
Some of the IR faculty when it's done.
Yeah. So why don't you go to the UCLA one and see if that has.
so many tabs.
So if you scroll down, maybe click on beginning compound 1. Are they giving you So why don't you guys come look at this spectrum? I'm gonna write this up here. So C3.
Take it with you.
I'll let you guys look at it. Is that right? C3H5BRO2?
So the conclusions I pretty much came to so far is that around 3,000-ish is where like your, I guess your methyl groups form for the most part.
Well, I would generalize it and say CH. So remember, the peaks that you see in an IR are a stretching peak. It's the stretch of whatever bond you're interested in. So in that region, you have CH, OH, and NH.
Isn't there a CH bond that's somewhere different though?
The aldehyde.
Is that the one at 3,400?
No, it's at 2,700.
There's one that was around 34 to 35.
There's a chart for it in your lab that shows all the different CHs and where they're at.
So keep that spectrum open, but let's work with this molecular formula first and see if we can. We're going to use that IR data to propose what major functional group is in this molecule. How many degrees of unsaturation are in this molecule? Remember, I think I mentioned this in class. See how that's odd? You have to get it to an even number. So a halogen will add to that count. So for CnH2n plus 2, that's what it should be 8, right? So this is what it should be. You sort of have to add that bromine, count it as a hydrogen. So you get C3H6. You get 1 degree of unsaturation. When you look at that IR, what stands out to you?
Carbonyl.
You have a carbonyl. Does everyone see that in that spectrum?
Is that the one that's between 2,000 and 1,500?
What's the exact number?
1717.
So 1717 is the carbonyl. That is equal to this. That's 1 degree of unsaturation, right? Now look in your molecular formula. How many oxygens do you have? 2. You've already accounted for 1, right? What's some functional groups you can think of that have 2 oxygens?
Ether. No, I mean an ester.
An ester?
Carboxylic acid.
Carboxylic acid. So now when you look at that IR, is there another clue to narrow it down between an ester and an acid?
There's no OH stretch.
You sure about that?
Is that the 3067?
That's
the big one.
the really broad one. You see how that?
I thought they dipped down a little bit. That is why I said that.
So one of the things I think maybe in life is students that you have to sort of get used to, in that textbooks give you a very sterile interpretation of life. You know, like they're going to give you, okay, it should look exactly like this, and that's what's like imprinted in your brain. But life is never like that. Life's very like gray and messy. So they're sort of going to look different, but in general they'll have the same shape. The acid's going to have a carbonyl and the OH. An alcohol will not have the carbonyl. an ester will not have the OH, but will have the carbonyl. So let's go ahead and say this has to have a carboxylic acid in it. What, you said it was like 3,200 or something?
3067.
So this is the OH. Those two are bonded together to make the acid. And so if you do this analysis, this is equal to CO2H. That's an abbreviation for an acid. C3H5, a Br, O2 is 1 degree of unsaturation. You've used up CHO2 is 1 degree of unsaturation. You have C2H4, a Br, and it has 0 degrees of unsaturation. How can you put these things together to get 0 degrees of unsaturation? You have 2 carbons, so you just draw that, right? So there's 2 carbons. Now you have, on that as it's drawn, there's 6 hydrogens, right? So one of them is going to be substituted with bromine. Then you're going to have another substitution. Say you draw it here. And that's where you would connect these two. So one proposal could be this. Is there another way you could bond those? So here I was pretty arbitrary. What if you had this? Then your molecule would be this. So let's look at these 2 proposals. Do they give you NMR data to consider?
Yes.
So before we click that open, let's see the unique number of carbons, unique number of hydrogens, the ratios. Then we're going to go look at the data, and you'll know right away which one it is. Trust me. So this first one here, how many unique carbons are in this first one right here? 3. How many unique type of hydrogens?
3.
What's the ratio?
1 to 2.
And then what about this bottom one? How many carbons? 3. How many hydrogens? What's the ratio?
2 to 1 and 1.
Not quite.
3 to 1.
So let's look at, you can't differentiate by carbon so much, right? Because they're both 3. The proton's both 3, but the ratios are different. So why don't you open up the proton? We'll see if we can figure out which one's right. So does everyone want to come look at what it's showing you? What did the ratio say?
2 to 2.
So what's it have to be then?
The first one.
Be the top one. borax.
Yeah.
You made it at home or something? Nice. Stress
Spell
re-
it out though, so it
Yeah.
makes sense now.
So that's I think the Notre Dame one's probably a good website to go to because you're given all the data. Then you can just go through them like that, and that's good practice. Again, you're probably like asking, what exactly do I have to know for this exam? And I understand that. But, I'm going to put up my shield and say, I really want you guys to form problem-solving strategies rather than feel like you have to memorize the shit out of a 1,200-page book.
Should we memorize all these though?
So those you have to. So when I say ether, you have to know the connectivity of atoms in ether or an alcohol or whatever. So I have time for one last question.
Before you go to another question, will you explain where the hydrogens are from the ratio?
Where they are, like this ratio?
I see where both of the twos are, but where's the one?
It's that one.
Okay.
It's
so
OH of the acid.
we just went backwards.
Yeah. So I know people have been wondering, should you write it 2 to 2 to 1 or 1, 2, 2 or 2, 2. When you read this spectrum, you can definitely write it in a certain order. If you're reading the spectrum from left to right or right to left, I would say maybe a better way of me doing this so it's not confusing is to just go 2 to 2 to 1. Therefore, you know exactly where they're at. So 3 to 1 to 1. And the big part of this is just carbon's the same, so it's going to be sort of hard to differentiate them. Although these unique sets are the same, these ratios are different. And that's how you would distinguish them. So again, if you care or if you don't care, the reason this is so important, people have won Nobel Prizes for I don't know if you invent this or you discover it, but maybe I'll take you guys, I'll show you the instrument before we leave. The reason this is important, for a molecule to lecture, if an OH group is moved one position over, that is a completely new molecule, right? And it does not have to have the same properties as a prescription drug. So the fact that, when you take a pill for whatever, it's pretty amazing the process of discovery from lab to market that pill has gone through. And the FDA, the Food and Drug Administration, has approved it. So it's gone through, if you've taken a name brand prescription drug, they've probably spent over $1 billion in research making that drug. So it's pretty wild. It's a lot of money.
What type of process do you have to go through to consistently create that same molecule over and over, to prevent it from, like you said, that OH group moving one bond over?
So sort of the research that I do is split into two areas in industry. There's medicinal chemists. They find the lead compound. And so they make variations of it. So they're testing, okay, should we put the group here or here or here or what? When they find the lead, then that's what they're going to go with. So the second group are called process chemists, and they scale it up. So they use these huge reactors. And at that point, the vessels you use are maybe 50 milliliters. So they're doing, 1,000-liter reactor. I mean, these are huge reactors. At that point, the process is known. The functional groups don't move at all. They're making that specific molecule.
I guess I'm asking how you make that molecule.
So the question of how. So right now you're learning how to communicate structure. The latter part of this semester, we're going to start learning reactions. How do you get a chlorine into a molecule? So if you have propane, CH3, CH2, CH3. How do you get chlorine in there? How do you displace the chlorine to get something else in there? So we're going to take just some pretty simple hydrocarbons, make them a little bit more complex, a little bit more, a little bit more, a little bit more. And that's the basis of what these people do. But knowing all this stuff is important now, is being able to classify carbons, hydrogens, because the reagents of the reactions that you learn are going to act in a very specific way. None of it's random. You will say, I'm going to react at that carbon versus this one. There's nothing, there's no voodoo about it. You will know. But we have to know all this stuff first. Any more questions? I'll try to upload this on YouTube. I'll send out, is everyone signed up for the Remind app? So I'll do another hour or so tomorrow at some point. If you have questions, my office is just over there. Stop by and ask. So I'll upload this on YouTube. I'll send out a Remind notification of when I have another one of these tomorrow. And if you have questions, just email me. And I'll try to respond pretty quick. But I'll show you the NMR, just so you can say you saw one.